Hello, I'm Mike McEwing. As a chartered engineer with 30-odd years of experience in both the military and the civil aerospace sectors, I'm now one of a select team of consultants delivering QinetiQ's air system sustainment programs. Over the next 15 to 20 minutes, I'd like to share my thoughts on sustaining air systems, consider the sustainment challenges presented by the COVID-19 pandemic, and illustrate one organisation's approach to sustainment reviews. I look forward to your questions at the end of the presentation. So without further ado, let us move on. As is often the case, it is worth considering what sustainment means, and then consider how it relates to our industry. The dictionary definition is reassuringly simple and leaves room for a wide degree of interpretation. However, the US military have helpfully provided some headers to help us understand what sustainment might actually involve. Most of the 9 principles are immediately applicable to aviation, common sense if you will, or indeed any complex support chain. What the principles don't mention is airworthiness and safety, which is at the heart of aircraft operations. Hence for me, air system sustainment is about airworthiness in the context of the wider support organisation. Without doubt, the COVID-19 pandemic is singularly the most disruptive influence on aviation in the past 50-odd years, and its effects are likely to persist for some time. As this presentation is being written, commercial air travel is starting a slow recovery. These are some of the images from the media and trade press from March this year. At the start were the restrictions in air travel in China rippling out to other nations, followed by quarantine, social distancing, and large-scale sanitisation. The downstream consequences are that demand for commercial flights has reduced. In April, departures were down by as much as 92%, according to Eurocontrol. Suspension of scheduled flights and airspace closures followed, and who could forget the sight of an operator's fleet parked up? This was the start of a chain of reactions and wider consequences. I've mapped the causes, effects and consequences here. It is a personal view, but I hope it provides both food for thought and shines a light on some of the relationships. Looking back at the principles of sustainment, COVID-19 touches on the majority of the principles. One could argue that all are affected. However, integration, simplicity and economy of effort are very much business as usual. Thinking back to my cause and effect graphic, there are several specific effects that are at the heart of sustainment. Firstly, lower utilisation. Now the CAMO or the Part M will develop or tailor an operator's maintenance schedule to reflect actual usage. However, the base data assumes a range of usage, and it may be that the fleet or individual aircraft are now below the usage expected, where calendar time becomes a more prominent metric than flight hours. A number of manufacturers provide high and low utilisation schedules, or at least the advice to help package the maintenance to reflect usage, but not all do. The same applies for aircraft that are parked. At what point does parking become storage or preservation? What is the impact of open-air parking or storage in the UK climate? What about humidity levels? Inevitably, there is a risk of environmental damage. Equally, what about the impact of long-term exposure to disinfectants? Some aircraft are being repurposed. They carry freight as opposed to passengers, but equally some are being adapted for aeromedical operations. How different is the flight cycle? Do they differ from those used to derive inspection frequencies? For example, an air ambulance use against a commuter aircraft use. Operation at lower altitudes or in marine or saline environments also has an impact. It's understood that there's some consideration for the equivalent of a scrappage scheme to retire older and thus less economic aircraft. However, there's no indication that these are likely to be in place in the near term. Thus, it's likely that a combination of lowered oil prices, which are currently 60% below where they were this time last year, and the lack of revenue for investment will mean delays to new aircraft deliveries. And these older aircraft will be run on. Older aircraft can challenge the supply chain, given the shorter product life cycles these days. As a result, components may need to be harvested from aircraft that have been retired from service. Lower revenue could also incentivise the use of low-cost maintenance providers, and therefore the feedback to type certificate holders. Indeed, our experience is that once outside of warranty, feedback on aircraft to the type certificate holders is minimal, apart from that either as a result of mandatory occurrence reporting or via their own service centres. Now, these factors typically are considered in isolation, which brings us on to the challenge of integrating these factors. I'm going to use the United Kingdom MOD's Ageing Air System Audit as an example of how to integrate the different strands associated with sustaining air systems. Sustaining older aircraft structures is well understood following a number of notable occurrences, such as the Aloha Airlines Boeing 737 in 1988. Similarly, the issues associated with electrical wiring installations was highlighted in the losses of TWA Flight 800 and Swiss Air Flight SR 111 in 1996 and 1998 respectively. As a result, the civil design codes for commercial aircraft now include a responsibility to consider the widespread fatigue and the integrity of aircraft wiring. The nature of deterioration is insidious, particularly where apparently unrelated aging effects can coincide. As an example, the fire associated with SR 111 was ignited by deteriorated wiring, but spread by deteriorated thermoacoustic insulation, where the fire retardancy diminished with time. Of note, that aircraft was only 7 years old at the time of loss. The purpose of the Ageing Air System Audit is to assure integrity as a system ages. The crash of XV-230 and the loss of 14 lives over Afghanistan in 2006 led to the Nimrod Review by the then Mr. Justice Haddon Cave. The review considered the wider circumstances of the loss and brought the challenges of operating older aircraft into sharp focus. One of the outcomes of the review was that the remit of ageing aircraft audits was expanded progressively from structures to include onboard systems, propulsion, airworthiness and support arrangements. The key points to bear in mind for AAA are that it is holistic and it does look forward across the remaining service life, and it is repeated at 10-year intervals. It considers design, maintenance and management across the supporting enterprise, that of product, processes and practices. The review team are independent, and this helps to avoid optimism bias and also provides a fresh set of eyes to avoid or at least identify normalised behaviours. As the slide notes, ageing isn't just a physical tangible attribute, it affects the intangible as well. The people aspect referred to here includes skills, knowledge, training and motivation, and indeed the Aloha accident included a number of human factors that contributed. This network illustrates a number of the data sources that a AAA would consider in terms of identifying age-related deterioration and illustrates some of the interrelationships between product and the supporting infrastructures. You will note that the sources include design and in-service data, as well as feedback gained directly from staff, the aircraft and the wider organisation. For those unfamiliar with the term, organisational stability refers to a combination of staff turnover, experience and knowledge, something that is well recognised in the civil space through Part 145 and Part M. The AAA team have broad experience of operations, maintenance and management, plus they bring individual subject matter expertise. In my case, safety assurance, propulsion and flight systems, such that the wider impact of changes is considered carefully. As an example, changes in flight profiles are traditionally considered to affect structural maintenance. However, there may well be an unquantified impact on engine or propellers or other systems. Similarly, the routine change in role for some aircraft may also introduce wear into structural attachment points as a result of poor installation instructions and maintenance practices. So AAA is both an art and a science, data-based but reliant on experience and knowledge to discern how the dots are joined. A AAA will always consider type and continuing airworthiness and will include a physical condition survey. If warranted, It may also include a zonal hazard analysis or forensic examination of ex-service components, structure or wiring. There is no direct equivalent in the civil space, although some of the elements of AAA are mandated, structures and aircraft wiring, through certification standards and design organisation approvals for large aircraft. Or they are considered in regulatory oversight activities, such as airworthiness reviews or aircraft continuing airworthiness monitoring. However, the reviews tend to be either organisation or product focused and do not extend across organisational boundaries. One would reasonably expect the majority of operations to be covered by existing instructions for continuing airworthiness. However, there are non-standard operations, for example pipeline surveys or air ambulances and the utilisation of civil aircraft in military roles. While these may fall within the published flight envelope, they may well fall outside of what the type certificate holder assumes typical usage would be. For example, sector length, unpressurised flying, manoeuvre ranges, and the same actually will go for little used private aircraft as well. Hence my belief that some form of a sustainment review is beneficial, and indeed more so in the current COVID-induced conditions. QinetiQ has over 15 years' experience in AAA and has conducted them across a wide spectrum of aircraft types, from historic aircraft such as Spitfires and Lancasters, through combat aircraft such as Typhoon, Tornado. It's looked at training aircraft, support helicopters, civil and civil derivative aircraft, gliders and so on. More recently, we've been engaged to assess aircraft that are maintained under civil as opposed to military oversight. What isn't evident from this graphic is that each AAA is tailored to both the type under consideration and also the wider operating and support context, as opposed to being just simply a standard or a boilerplate solution, such as a checklist. Now, what I'd like to do is to share some more recent findings with you. So first, let's look at unmonitored and unconditioned components and a change of usage. And we'll also consider integration and interfaces. So the first one is flexible hoses that carry flammable fluids. Now, one of the reviews identified that hoses had recommended lives and that were aligned with the original service life of the aircraft, which was subsequently extended. Although some hoses had been replaced, these were neither identified as lifed items nor records retained of replacement. Hence, there was a risk of leakage or rupture. In the interim, best practice had evolved, but had not been taken into account in maintenance schedule reviews. There was also a loss of corporate knowledge due to a series of location changes, and there was significant churn in staff. The condition survey at the time identified a 40-year-old elastomer hose and a brake system. Thinking about change of use, one of the reviews established that its future use would include embarked operations as the norm. Now, the aircraft operator was considering adding flotation gear, but there was no intent to modify the landing gear, and when we looked into it, the design assumptions catered for heavy landings on land, but they didn't consider the implications of being lashed to a rolling deck and the loads that were going to be introduced through the landing gear into the backup structure. There'd be no testing or certification. In terms of integration and coherency, in one aircraft fleet, we found that there was a policy to conduct a 6-monthly review of corrosion arisings on this particular aircraft. It's quite an older aircraft. However, in practice, this pan-organisation group had not actually convened for 3 years, and in that time neither deteriorating condition of the aircraft was identified, nor the effectiveness of the anti-deterioration measures, where they certainly weren't challenged. Again, the condition survey confirmed the presence of significant corrosion that was actually unknown to the Aircraft Operating Authority. We'll cover now a few examples from the condition survey. The survey is more in depth than a typical airworthiness review, and it does uncover a range of conditions indicative of a deterioration in husbandry standards, issues with design or installation, or an ineffective maintenance policy. As you can see here, fire blankets are soaked with oil or pipe clearance, or indeed exposure of a conductor, leading to degradation in standards of safety, possibility of a fire hazard as well. We've also found pooling of water, possibly as a result of the environment, but also potentially because of an aircraft wash. And the corrosion, again, the corrosion and cracking of connectors. These are more pointers towards the acceptance and indeed normalisation of the deteriorated condition and a loss of an understanding of what good actually looks like. Again, our focus here is safety, but also about availability and the additional work required to rectify it. A small amount of preventative maintenance avoids a lot of corrective maintenance. Let's look now at zonal hazard analysis. This is one fixed-wing aircraft. Again, it's an illustration of how hazards arise in the as-flown or the as-maintained state. In this case, grease accumulating in a liquid oxygen bay. Liquid oxygen and grease is really not a good mixture. It's spontaneously combustible. Also, a control restriction because of where do you stow a cargo light and the attendant cables, and you can see there that the flight control system cables are exposed. In terms of rotary wing, here we've got some hot surfaces that are exposed due to deterioration in insulation and also chafing of electrical wiring on pipework. The left-hand image indicates the interaction of human elements. It's a no step, as you can just about make out, but it's clearly a convenient step up judging by the wear. The middle image is more maintenance-induced deterioration, taking the insulation off, putting it back on. And the right-hand image is more about installation. But was that as design intended or as part of a subsequent installation or modification? And again, there are recent examples of wiring and pipework interference causing fires on both military and civil aircraft. So to conclude, a sustainment review addresses this question: how effective are your support arrangements in countering the threats to airworthiness and the safety posed by ageing? What we've seen is the review, the extent, it's flexible, but it certainly should consider how the aircraft, the operations, and the wider environment have changed over time. It should be independent of those directly involved in the operations, maintenance, or management. The likely outcomes are improvements in safety, availability, and cost of ownership. We believe that sustainment reviews do add value. They do take time, but ultimately it is about making sure that aviation is and remains safe. Thank you for watching. I look forward to your questions.